So let's start.
Okay, so Ole, are you starting with the introduction?
Okay, thank you. Welcome everybody to this bit special meetup. And yeah, want to start with our first talk I live in Fritz from A to B. And yeah, it's about Go compiler optimization, and let's hope that this will work out for all of us. Thanks and welcome a lot, Levin, and yeah, please start.
Okay, so before I start with the talk, I just want to apologize for the mess with the first call. Yeah, we weren't as well prepared as we should have been from A to B. But anyways, at least we can have the two talks. Yeah, so I'll start with my talk, which is titled, Will It Optimize? And it's about optimizations in the Go compiler. So the idea for this talk is something I got from a blog post from almost 10 years ago, which is also called Will It Optimize? And this blog post talks about optimizations in the GCC compiler for the C language. Yeah, so when I saw this blog post, I thought it would be fun to do something similar for this, but sort of updated and for Go in 2020. Yeah, so that kind of evolved into this talk in the end. So to give a bit of context, in Go, every time you compile your Go code, the compiler performs certain optimizations. So it transforms your code or your program in some ways that make it more efficient, but that don't change the meaning of the program. And in Go, this happens always. So you don't need to pass any special compiler flags. It is just done by default. I think most, let's say, experienced Go developers have some idea of what happens with those optimizations, but most of us don't really know, like in concrete terms, what is the compiler going to do. So when I started preparing for this talk, I came up with a list of some optimizations that I thought the compiler might be doing. And some of these are sort of common optimizations that you can find in the computer science literature, and some of them are more specific to Go. And then what I did for each of them was to write some simple example code that would serve as sort of an experiment to let me see if the Go compiler applies this optimization or not. And yeah, just in case it's relevant, I've tested all of this with Go 1.14, and I compiled for two different architectures, for AMD64 and ARM64, and all of it on Linux, although I don't think that really makes a difference. Yeah, so for this talk, I want to make it a little bit interactive, so to sort of involve the audience. And the format I've come up with for that is that on each of the slides for an optimizations, I have two code samples. On the left is the code that a programmer might have written, and on the right is an optimized code, which is meant to show how this optimization transforms the code in the compiler. And I want to invite all of you in the audience to take a look at the sample and think about what you think. Is it going to apply this? Is the Go compiler going to do this or not? And if you think you know it, or maybe you just want to make a guess, then please type in the chat window in Zoom. Yes, if you think it's going to do it. Yes, if you think it doesn't. And then there is a third option. I've included one sample where it's a bit of a trick question. So in that case, the transformation is actually an invalid optimization. So it makes the code faster, but it also changes the meaning of the code. And then obviously the Go compiler doesn't do that. Yeah, I also have a couple of slides where I show how I did those experiments to find out if the compiler does these optimizations, since I thought that might be interesting as well. Yeah, so we'll start with the first optimization. So this one is about how integer multiplication is implemented in how the compiler sort of implements integer multiplication. So if you look on the left, there's a very simple function which just takes an integer and multiplies it by 2. And on the right is an optimized version of that, which uses a bit shift operation instead of the multiplication. So for those of you who are not familiar with that, or maybe learned it at some point and forgot it, what this particular operation does, so a left shift by 1, is it takes all of the bits in the binary representation of the number and moves each bit 1 position to the left, and then the rightmost bit becomes a 0. And in effect, that does the same thing as a multiplication by 2. And it's typically a faster operation, just the way it's implemented in CPUs. Yeah, so my question to you, do you guys think the compiler will do this? Yes or no? Okay, so a mix of yes and no in the chat. So the answer is yes. I think this is quite simple to implement to detect this case. And so the Go compiler will do this for multiplication by 2, or also for multiplication by a different power of 2, so 2, 4, 8, and so on. Okay, so we move on to the next one, which is almost the same thing, but sort of done in reverse. So for division by 2, doing that as a bit shift by 1, but instead of shift left, it's a shift right. So is the compiler going to do this? No, yes. So I think Ole was on the right track before, actually. So this one is the trick question. That's actually an invalid transformation. And to see why, we have to look at what happens with negative numbers. So for positive numbers, this kind of transformation works just fine. But for negative numbers, this example, or the couple of lines of example code here show what happens. So if we calculate in Go -3 divided by 2, that works out to be -1. Because with the rule in Go is that with an integer division, it always rounds towards 0. So for positive numbers, it rounds down, but for negative numbers, it actually rounds up. And the way the right shift works out is that it always rounds down. So for odd negative numbers, that returns a different result. Yeah. And yeah, so here I just want to show you quickly how I figured this out. No, there's not going to be a quiz at the end. This is the quiz. Yeah, so when I started with this, I thought maybe I'll just read the source code of the compiler and figure out what it does exactly. But that turned out to be a little harder than I anticipated, and I didn't quite want to invest that much time. So one thing I did to figure out what happens is to pass a flag to the compiler, to the Go compiler, that made it print out assembly code. So assembly code is sort of the last step before the compiler transforms your program into actual binary code. And assembly code is pretty hard to read, but even if you don't really have a background in assembly, you can often sort of guess what happens. So in the example I have on the slide, this is the code for the x times 2 calculation. And what's highlighted shows how this is implemented. And it's this SHLQ $1AX instruction. So SHLQ is a shift left operation, and then $1 is the constant one. So that is a shift left by 1. Yeah, so let's move on to something that's a little more Go specific. On the left, we have a function that takes a map, looks up 3 values in the map, and then adds them together. And if you look closely, it does the same lookup twice in a row. So this is kind of inefficient. We could just do the lookup once, so that in variable, and then use that variable twice. So that's what I've done on the right. So do you guys think the Go compiler is going to do this? I see one invalid. Yes, no. I don't think this is invalid. I don't see, I mean, the map is not going to change in between those two lookups. Okay, so the answer is no. When I tried it out, the compiler actually put two identical lookups into the code. Yeah, I'm not sure why that is. I guess maybe this just doesn't happen that often in practice. Yeah, so this example looks a bit more complicated, but the idea is actually quite simple. So on the left, we have this function square, which calculates the square of x, so just x times x. And this is called once in f inside a loop. So in this case, it makes sense to just take this calculation x times x and put it right into the f function instead of calling a separate function. So that's what I have on the right. It's just taking the contents of square, this x times x, and put it right into the function f. So do you guys think the compiler is going to do this? Yes or no? Okay, quite a few yeses in the chat. And you guys are right. The compiler will do this. This is, I think, quite an important optimization, and it's actually useful for two reasons. One is that we avoid the overhead of a function call, and the other one is that it often opens up more opportunities for optimizations, since basically after inlining, the compiler can apply some optimizations that sort of go across the function call boundary, since the code is then all together. So we'll stay with function inlining for now, but this next example is a more complicated course of function inlining. And what it is a function that calls itself, so a recursive function. Yeah, if you look at the code on the left, in case you're wondering, this calculates an approximation for the square root of x. But you don't really need to know that for the optimization. So basically this f calls itself in the last line. And yeah, inlining recursive functions is obviously not that easy, but in that case, it's not too bad because the recursive call is the very last thing that the function does before it returns. So in that case, there is a simple way to turn that into a non-recursive function, which is what I have on the right. So the if part is the same as before. And then what the function does is just update the function parameters to the new values and then jump back to the beginning instead of calling itself with those new values. So is the compiler going to do this? Yes. Yeah, someone in chat is saying this is called tail recursion, which is correct. Ole's answer is hopefully. I'll have to disappoint you, Ole. The Go compiler does not do this. Yeah, I think so. So this tail recursion or tail call elimination is very common in functional languages, where it's actually very important to make them efficient. And it's also done in some, let's say, non-functional languages, but the Go compiler doesn't do this. And I think the sort of the reasoning behind that is that functions like the one on the left, so these simple recursive functions, are not really the way you would usually write code in Go. So it's, at least in my view, this is not really idiomatic Go code. So it also makes sense not to optimize it. But that's just my opinion. I can't really speak for the Go developers. Yeah, and the experiment for this one is quite a lot simpler than trying to read assembly code. So the Go compiler has a flag -m, and then if you use Go build, you can use that by compiling with -gc flag equals -m. So gc flag means pass these flags to the Go compiler, and that prints out information about optimization decisions that the compiler is making. And one of these is when it inlines functions. So in this case, we can see very nicely on line 8, the compiler decided that it can inline square, and then on line 15, it decided that it will actually inline it. Okay, so the next one has a very complicated name, but it's actually a pretty simple idea. So common subexpression elimination means if we have a function that does some calculations and there's one bit of calculation that's repeated, that's 2 or more times, then we can just do that at the beginning, assign the result to a variable, and then use that variable in there. Yeah, so in the example here, the b times c is, it's in there twice in the calculation for a and d, and so on the right, I've just pulled that out into a separate variable. So who thinks the Go compiler will do this or will not do it? Yes, okay, mix of answers. The answer is yes in this case. Compiler will do it. Yeah, I think that's one of those pretty basic expression optimizations that the most modern compilers will do. Why? So someone's asking why in the chat. The answer is that with the code on the right, we have only one multiplication at runtime, so that just makes it faster. It's just fewer calculations to be done. Yeah, and then we have another one that's Go specific. And for that, I first need to explain a little bit about how slices work. I guess most of us, you will know that, but maybe not everyone. So when you index a slice, so you take an element out of a slice, in Go, if you use the wrong index, so the index is too large and there's no element with that index in the slice, that creates a panic. And to make that work, the compiler actually has to put in 2 instructions for each indexing operation. One is a bounds check to check if the index is out of bounds, and then jump to the code that creates the panic, and then the code that actually gets the value out of the slice. Yeah, so there are cases where the compiler can avoid this though. So if you look at the example on the left, after we look up S4, we know that the lookup to S3 will be fine because 4 is higher. So the slice must have at least that length when we get to the line S3. So do you guys think the compiler is smart enough to recognize this and then generate different code for the second line? People are guessing no. People are guessing yes. Okay. The answer is yes. The compiler is actually smart enough to do that. Yeah, I guess this optimization helps a bit to make up for the fact that array lookups, which are basically a very simple operation, that they have some overhead in Go. Okay, and yeah, so the next optimization that's the only one I have, which is not about optimizing a function, but optimizing a struct. So you have to look pretty closely here actually to see the difference. So in the struct on the left, we have 3 fields, X, Y, Z. And on the right, we have the same one, but the order is different. It's X, Z, and then Y. Yeah, so to explain why this is even a useful optimization, I have to explain a bit how structs are laid out in memory with Go. Yeah, so I have these little diagrams which kind of show how this how a struct like this would look in memory. So each little square is 1 byte, and if we start on the left, each of the blue squares is that's where X, Y, and Z are stored, and then the gray squares in between those are sort of left empty, and the bold border, that's the struct as a whole. So the reason why we have these weird gaps has to do with how the processor or the CPU loads data from memory. So when the processor loads an 8-byte integer, like the value y here, from memory, it kind of wants the data to be at an address with a multiple of 8. So it's kind of, it can sort of take this block of 8 aligned to a border of 8. Yeah, otherwise it's either not allowed or slower, depending on the architecture. Yeah, this is on AMD 64. On a 32-bit architecture would look a bit different. Yeah, but that explains why the version on the right is better, because if we first put in the two booleans and then the int, then we don't waste as much time. It's actually one third smaller in this case. Yeah, it's definitely different between 32 and 64-bit architecture. So I'm assuming this is AMD 64. Yeah, it's a few answers already. Some yes, some no. Any more guesses or opinions? Okay, the answer is no. I'm actually not 100% sure if this is no or if this is actually another invalid transformation. I took a look at the Go spec, and it doesn't say anything explicitly about about how structs are laid out in memory. But maybe that's kind of something the Go developers want to guarantee anyways. Yeah, so for this one, it actually makes sense to do this manually if you want to optimize memory use. Yeah, and the way I figured this out is actually by using something that's part of the Go standard library, which is the unsafe package. So that has two functions that are very useful for this kind of thing. So one of them is unsafe.offsetoff, which tells you how far inside a struct one of its fields is. And the other one is unsafe.sizeoff, which just tells you the size in bytes of any variable. Yeah, so when I ran it for the code sample, sort of the non-optimized code sample, it showed 0, 8, and 16 for the offsets, and so then you can see they are all aligned by 8 bytes, and it didn't do any reordering. Yeah, so I think then we already come to the last optimization, and this one is about loop invariants. So the idea here is if we have some calculation inside a loop that we can move out of the loop, then that will make the program more efficient because we avoid doing this calculation over and over. So on the left, the function takes a slice and two values, x and y, and then it changes each element of the slice by assigning x times y. And this x times y, that part of the calculations, that's never going to change inside the loop. So we might as well do that first, assign the result to a variable, and then use that variable in the loop. So yeah, already some opinions coming in. Any more? Okay, I see one no and a whole bunch of yeses. I think you guys are going to be surprised by the answer. And in fact, I was also surprised when I tried this out. And the first surprising thing is that the outcome here depends on the target architecture. So I tried it for AMD 64, and there it does not do this optimization. So code on the left is compiled the way it looks with the multiplication inside the loop, and the code on the right is also compiled the way it looks. When I tried it on ARM64, there was a bit of a surprise, which is that actually the code on the right gets compiled like the code on the left. So it actually moves the multiplication inside the loop, which seems very strange. Like intuitively, this is not an optimization, it's a pessimization. It just goes the opposite direction. I can't tell for sure why this is. I mean, I'm not exactly a compiler expert, but I have an idea. And the idea is that I saw when I looked at the assembly code for the ARM64 version so it has the multiplication inside the loop, and the way this is compiled on ARM64 is with a FMA instruction. So ARM has this fuse multiply add instruction, which does an addition and a multiplication in a single CPU instruction. So that makes this kind of calculation more efficient. And my assumption is that the compiler somehow sees that it can do this calculation quite efficiently on the target architecture with a single instruction, and then decides to just pull that into the loop so it can use this instruction. Yeah, this one was a bit of a surprise. Okay. Yeah, so what's the conclusion for all of this? So the Go compiler does quite a few optimizations, which is very nice since that makes our code faster, but it's actually less than a lot of other compilers. So if I go back for a moment to the original Will It Optimize article, the one from 10 years ago using GCC, one of the examples in that architecture, in that article, was about doing function inlining for recursive functions. And his example was actually a function that was not tail recursive. And the answer was still yes. So GCC was able to inline this recursive function, even though it's kind of one of the harder cases. So it looks like, at least to me, it looks like GCC, even from 10 years ago, was doing more advanced optimizations on, than Go, which seems like a bad thing at first glance, since Go is not optimizing our code as much as it could. But I think in the end, this is about trade-offs, like a lot of things in software engineering. So more optimizations would mean faster code for us, but on the other hand, more optimizations would make the compiler more complex, which means there's a higher chance of bugs in the compiler, and it makes the compiler slower. And I think for a lot of us Go programmers, the fact that the tool chain is both fast and reliable is actually one of the big advantages of Go. So I think overall, being conservative with optimization is maybe a good thing. Okay, so thank you for your attention. And yeah, thanks again to the original article. You can check it out on a website called ridiculousfish.com, or if you just Google for Will It Optimize. Yeah, thanks.
Thanks.
Ole, are you going to take it over again?
Thanks a lot for the nice talk. And